I'm actually on the screen. On paper, I am actually a cloud DevOps engineer, but it sounds a little too hipster, so cloud networking engineer is what I'm going to go with. My address is there if you want to spam me with things I will happily ignore. So we're going to be talking about OpenStack networking high availability challenges, and there is a lot of serious business ahead. This is there'll be dragons in these waters. So we're going to talk about what exactly is OpenStack networking, and I'm going to move through this a little fast just because I don't expect you to really grok everything that's going to be in this list, but I want you to get kind of a feel for the amount of components that we're talking about. So we have Open vSwitch bridges, we have OpenFlow rules, Linux bridges, IP tables and EB tables rules potentially, virtual Ethernet pairs, also known as VETH pairs, DNS mask, which is serving as DHCP and also DNS forwarding, an EC2 compatible metadata service with proxying, network namespaces, network overlays. We have GRE, the capability for VXLAN and VGRE. We also have VLANs and flat networking. Layer 2 virtual and physical switching, which is generally provided by the OVS bridges. We also have layer 3 virtual and physical routing, which is provided through an agent that we'll get to in a moment. So we have some extra services that right on top of these. Load balancing as a service, VPN as a service, and firewall as a service. And there's also some other as a services. So TLDR, it's complicated, very complicated. So the services, they kind of break down. I'm going to be talking about Neutron here. The previous version of OpenStack, which was Grizzly, the release version, used Quantum for its networking name. They decided to change the name because Quantum is owned by another company and they would not sell the rights. So it's now Neutron. So Neutron server, this is the API server, fairly self-explanatory. We have a DHCP agent. This helps orchestrate DNS mask. We have a metadata agent. This actually orchestrates a proxy to allow your instances to talk from their potentially overlaid networks into your actual EC2 metadata. And the L3 agent, this allows for virtual routers, software routers that can interact with OVS and do SNATs and floating addresses. And then we have a plugin system in Neutron. And this plugin system allows you to implement layer 2 switching and bridging in a variety of ways. You can actually have plugins that will talk directly to a piece of hardware, a physical switch, and actually set up VLANs and do other interesting things for you. So in this case, we're just going to be referring to the kind of vanilla OVS plugin. So this assumes that you have Open vSwitch running on the machine and it actually sets up an Open vSwitch bridge for you. And then again, a whole bunch of other agents, and there's all kinds of stuff. This is just kind of a scratching the surface. So looking at an example infrastructure for OpenStack networking, if we just look at something fairly simple, this is pretty pedestrian. We have a public network up top and some kind of top-of-rack switch that's not really in our OpenStack environment. We have a couple of software routers, 2 tenants. So in this terminology, tenant is kind of the same thing as a project or a group that has users inside of it. So inside of each of these tenants, we have a subnet. And so there's net 1 and net 2, and each of these nets have their own subnets. Here, they're not overlapping, but these are actually isolated in such a way that they can overlap. So you can have any internal subnets you want. We're not going to dwell on that too deeply because that's kind of beside the point of this. So if we move on and we look at something horribly complex, so this is actually what a compute node looks like on the inside. And there's no namespacing here. On an OpenStack compute node, and you actually do like an IPA or ifconfig if you haven't learned that ifconfig is outdated. You'll see a number of interfaces that are horribly named and very confusing. Those X, Y, Z, Ws, etc. there, those are actually UUIDs. So it's going to track them by that. It's very unscrutable when you glance at it. I know I'm just making an awesome case for using OpenStack here. So the tooling that exists and the API that exists is a little nicer to use. There's still some rough edges, but it's a much nicer. So this is kind of how it's structured. Part of the reason why we have this Linux bridge sandwich here, you see VMs at the top, their internal interface, and the device that is bridging the VM, the tap device. So you've got a VNet on the outside, And then there's this QBR, this Linux bridge in purple. And it is attached via a VETH pair in the brown into this BR-int. vSwitch integration bridge. Everything plugs into the integration bridge because it integrates everything together. And the QBR exists there because in OpenStack and Neutron, they wanted to have the ability to have security groups. So policy, filtering, rules around who can talk to what and who can't. And they didn't want to implement it in OpenFlow. As a quick aside, OpenFlow is a simple stateless rule system for switches that OVS, Open vSwitch, implements, and it allows you to do, again, very simple things that can result in complex topologies, flexible topologies, but that's all stateless. So if you want to do certain types of stateful filtering, or even just filtering that's more consumable for somebody who knows Linux, they wanted to use IP tables and possibly EB tables. So they came up with this system to sandwich a Linux bridge in between your VM and your integration bridge in OVS, and using a Linux bridge means that you can actually target it for IP tables and EB tables because it can recognize traffic going through a Linux bridge. So we have internal VLANs in this OVS bridge, port VLAN, tag 1, tag 2, and as it helpfully shows in this diagram, the tenant flows, flow being communication of traffic, often TCP, are separated by these internal VLAN IDs. And then we have another VETH pair that connects this integration bridge with a physical provider bridge, helpfully named BR-ETH1, referencing the fact that it actually is bridging a physical interface named ETH1. So these OpenFlow rules, like I mentioned, they kind of show them in these bubbles on the right. Very simple version that if the internal VLAN, going one way is 1 or 2, it will actually change the packet to the frame to have the correct tag for once it leaves the box physically. Very simple, right? Very straightforward. Okay, so on a network node, this is where the services live, a lot of the agents live. So we have DHCP, L3, metadata, and it's kind of similar, but we actually have namespaces here. And they're not pointed out in this slide, they're actually going to be on the next one. So the namespaces are highlighted in these blue squares here. So if you just kind of imagine that there's blue squares around those. So essentially this is very similar. We have an integration bridge, we have this VETH pair to physical bridge, and then kind of going up it's a little bit different now. Now we have these namespaced things. And DNS mask is an actual process running inside of the namespace. And these namespaces are connected with these tap devices, and essentially it's like a cable. It's very similar to the VETH pair. And this allows you to broadcast into the namespace. So that process, that DNS mask process, is actually listening on an interface that looks like it's the only thing that exists on the box. And it has the address of the DHCP and DNS server, which is provided by DNS mask. And so your instances across the private network, through the bridges, possibly through tunnels, can actually broadcast into DNS mask and get a DHCP IP. So it's very complex as a stack, but the end result is a very normal looking user experience. So moving along, again, namespaces are here. They have names, QRouter, QDHCP. Even in Neutron, it's still QRouter, QDHCP. Pretty straightforward. If you're not familiar with namespaces, you can use the IP route tool on Linux, which is the binary name is IP. You can do IP space net in S or just net, and it will show you the list of namespaces. You can run commands in there. You can even spawn a shell in there, which is actually pretty handy for troubleshooting. Just run bash inside. So, did I mention it's complicated? Because it really is. It's very complicated. Yeah. So, I work for Rackspace, as I believe was mentioned, and I work on the private cloud team. My slides are talking to me. What exactly is it I do here? So I am the network guy. I also do a lot of development, wear a lot of hats. That's why my title is technically DevOps. But really what I guess my primary role on the team is to deal with Linux networking. That's an area of expertise that very few people have, not trying to toot my own horn, but it's actually just a lot of archaic knowledge that's very tribal. So learning it all and figuring out how to apply it is very difficult. Okay, all right, like you're very useful. All right, thanks, slides. Okay, I think we might delete this later. Now it's threatening me. Okay, all right, so moving along. So high availability. What is high availability? What does that mean? He is highly available. Wide open. No, a little more seriously. High availability. So we usually mean something along these lines. There's lots of definitions. There's lots of arguments about what exactly is meant here versus redundancy, or even just availability versus high availability. So here's how I'm going to define it for the purpose of this talk. It's very simple. There is no single point of failure. Okay, that's very vague on purpose. Service availability, even under failure conditions, very vague, but it'll suffice for the moment. We can fail over access from one side to another for some definition of fail over, possibly just fail in addition. So it is made of many components that are working together. And I'm going to talk about how our product that I help design in this area specifically works and how it's solving problems that we ran into. They're actually extremely difficult to solve in a straightforward way, which is unfortunate, but 6 months worth of bashing my head into the wall has resulted in learning all of the unfortunate ways that it's difficult. So this is going to be a brief list of components. This is how we're solving this problem. We're using Keep Alive D. It's basically a VIP state machine. It's usually used for failing over VIPs between a pair of controllers or a cluster of controllers. You can also just use it to fail over state only and not actually manage IPs, which is kind of where we're going with this. Using network namespaces, very similar to what OpenStack already uses. Standard routing. There's no policy routing here. I started down that path and it was not quite doing what I wanted, so ended up a solution that has standard routing. We are using proxy ARP. If you're not familiar, it proxies ARPs. Really is not much more complex than that. You basically tell Linux, this interface and this interface, I want you to proxy ARPs between. And if it has routes to the networks that are attached to both sides, when it gets an ARP request on network A, it will send the ARP request, it will proxy it to network B. When it gets the response back, it stores it in its ARP table and then responds from itself back to network A, which is the key part. So if you have some reason why network B can't be bridged directly into A for ARP requests, then this is your solution. That would be a MAC filtering case, for instance, which if you're running cloud in a cloud for testing, for instance, you often run into MAC filtering. This is how I discovered this issue. IP tables NAT. It's pretty straightforward, just DNAT and SNAT. HA proxy is part of our solution for service load balancing, so API services. We're also using TCP keep alives everywhere we can, and this is very important. I'll get to that in a little bit, but TCP keep alive, if you're not familiar, is really just a flag. It's an option on a socket when you create a connection that says, every once in a while, if no traffic is passed, I want you to count down, and when you hit the end of this timer, go ahead and send out a little probe on the connection and see if it's still active. And if it isn't, increment a counter one and wait again, try it again, and if the counter hits, X, then kill the connection because we haven't received anything back. This is important because TCP connections by spec can stay active for more than 2 days with no traffic, which is not what you want during a failover, turns out. You don't want them to think they're still connected for 2 days. That's a pretty slow failover. So we're also using a PIPA, point-to-point addressing. This is the 169.254/16 range. Not everybody's familiar with that. You might see it randomly when you don't get a DHCP lease on your laptop from your router. But it's automatically provisioned IP addressing. Yes, I used addressing twice. It's like an ATM machine. But we're going to use this for a very specific reason. There's some unique qualities to a PIPA addressing that, I just did it again, that allow you to have duplicates of these addresses on several machines that are in the same broadcast domain, and there's not actually an issue. That's kind of hackish, but it's awesome. So the rationale behind why I developed this solution. Hopefully these are not all going to be too small to read, but our RPC, OpenStack controllers are very unique from a networking perspective. I'm going to try not to just read the slides. We actually are doing something horribly dumb, and we're doing it for a good reason, and so is everybody else. Everybody else has this problem too, but our controllers meaning where we host our API services, and we actually combine, in our case, the network node that I mentioned earlier into our API service node. So we have all of our services on one pair of machines, our controllers. So these run our Keep Alive D, our HA proxy. They have our VIPs for services, and they run both the services and some clients, which themselves are also services, because OpenStack's kind of inbred like that, on the same machines that are load balancers. This is a terrible idea. You should never do this. There's a lot of stuff that goes wrong and catches on fire. Like, you should never have clients and services talking to each other on the same machine that is load balancing the VIPs they're talking on. It's not what you want, but it's what we're doing. So, moving along. Usually your load balancer is a standalone host, right? You got an F5, got a Zeus box somewhere, or a NetScaler or whatever. That's fine. Like, you're always going to have some kind of remote to local or local to remote connection. There's never a local to local, right? Nothing's on your load balancer. If you said to somebody, hey, can you go ahead and install, like my new app on the F5, they'd look at you like you were nuts, because you are. Don't do that. It's not what you want to do. So our controllers, as mentioned, have a mixture of everything. It's great. So, as I discovered, you can spend months, literally, trying to solve the problems that arise. Now, in our case, I was trying to solve these problems for both of the platforms we support, which is Ubuntu and CentOS, without increasing our node count. This was the trick, right? Because I could have made a couple of load balancer boxes and problem solved, we're done here. But we actually have a minimum target of 3. 2 controllers in an HA configuration and 1 separate compute node. This is what we sell to our customers as our minimum supported configuration. So this is what they buy from us as the smallest cluster. They go up from there. We can split things out later, but I needed a solution that worked for this for both platforms. So it colored a lot of my decisions. So, as mentioned, didn't want to change the footprint or the system or network architecture. Like, we actually deploy for customers in their own data center, and we will use their gear and their networking, and then we'll support it, which is, we're insane, go figure. I'm not on the support team, and I'm glad for that. But that's what we do. People pay us for that, and they say, here's all my stuff, make it work. And we're like, all right, and you got money. So we needed this to work just inside of the machines, nothing outside, because we wanted to not have to dictate to a customer that you have to change everything you're doing and spend more money. So we don't want hardware load balancers required. We still need to work on both actual distributions and have simple enough pieces that as things change over time, it's not going to randomly break. That was my goal. It's a very, very simple goal. So what I'm doing primarily, just a little summary, is I'm using a network namespace to put my VIPs inside of. They actually live in this namespace. And so they always appear remote to the clients and the services running on the controllers as well as other boxes. So we're basically making load balancers. They're off on a rack somewhere in theory, but they're actually embedded in the same box. It's the high-level overview. So architecture-wise, these are my really well-crafted diagrams. We have a pair of controllers. They have a management/VIP network they can talk across. Very simple. We don't need anything more complex for this. So I have we have a VETH pair that's connecting the namespace inside to the namespace outside. Technically, in Linux now, when you just type commands that are networking related and you don't use IPnet and S, then you are interacting with the global or main namespace. This is the default namespace. You're always namespaced. It's just that this is where your physical connections actually live, and routes and IP tables and etc. So we make a custom namespace. We put this VETH pair. Again, it's just a cable. It's 2 interfaces that are tied together, and whatever goes in one end comes out the other. It's a cable. We put one in inside, one in outside, and yeah, it's a cable. So our Keep Alive D configuration is very straightforward. It's just VRRP to say virtual router redundancy protocol. It's the open source version of HSRP, which is what Cisco came up with, hot standby router protocol. Basically just lets you send messages, you advertise back and forth between two nodes over multicast, and whoever thinks that they're the master or should be in charge of resources is the one advertising out. So if you're listening and you think you should be backup and you stop receiving advertisements, now you have to elect whether you should be the new master or not. So you start sending your own advertisements. They might communicate a little bit, but it's essentially stateless. Essentially, if you're master, you ping. If you're not, you listen. Very simple. But what we're doing here, what I came up with, is to not have keep-alive-d actually apply VIPs in the global namespace. Instead, you can have on state transitions an arbitrary script get run. And you can also tell it, I have no VIPs, just do state transitions. So this is what I built. I built a script in keep-alive-d's config file to call scripts. It's called notify_state. So master, backup, fault, stop. So I called it notify.sh. Only the active side will have the VIPs. It's pretty standard. So ARP, lovely ARP. Since our VIPs are in a namespace, we have to get traffic in and out of them, right? It says route there, and that's what the solution I came up with was, but we just need to get it in and out. So routing was chosen because, again, MAC filtering, and there's other scenarios where bridging may not be appropriate. So I couldn't just bridge my namespace out into my physical and hope for the best. It works fine in some environments, and in others there's a lot of restrictions why that won't work. So I went with routes. Okay, routes are great, except for routes by default will not have ARPs because ARPs are broadcast, they're not routed. So I made use of proxy ARP and routes into the namespace, and that allows proxy ARP to work correctly. And then all the remote machines still think that, all the remote machines see the exact same thing. This machine still thinks it's remote because it's following a route through an interface. It's not on this box as far as that namespace is concerned. It's a little weird, but it's embedding another box inside. So this is fun. Inside of the namespace, we have DNAT and SNAT, and this is to allow our VIP traffic to bounce through. This is effectively the actual load balancing / VIP portion. Is anybody familiar with a full proxy load balancer, what that means? No? Okay. Full proxy means that you make a full TCP connection to the address, to the VIP, the service, and then the load balancer then makes another separate full TCP connection to the actual backend server. Non-full proxy means that it actually does some minor modification to the packet and sends it on. There's no actual handshake that occurs. So it's a single connection passing through. This is non-full proxy. We are passing it into the namespace. We're mutating the addresses in such a way that the client doesn't know it's not talking to a remote service, and the service doesn't know it's not talking to a remote client. So it's a little bit of ninja magic to correctly mingle the destination and source addresses so it looks right. And effectively what's actually happening there, it's what I just said. This is the translation. So you're a client, you're going to a VIP, and you're going to get DNATed to where your destination is actually the service IP. It's the back end, just like a regular load balancer. And then the source, as you go out, it was the client. Now it's going to be the VIP. It's going to look like your VIP is talking to your service and your client's talking to your VIP. So it's in between in both sides. And the reason why that is the case is because if we didn't change the source, when the service replied to the client, it would just talk directly to the client because it knows the IP is right there. It's right next to it. So we actually have to make it go back through the namespace so that this translation will get unwound on replies. So it's interesting. Works great, but it's very convoluted to look at. So we had another interesting issue. HA proxy binds to the service ports that you actually want your services to be on, but usually it binds to the VIP itself as the address, and then each of the ports for services, and then it will actually full proxy. HA proxy is a full proxy load balancer, and then it will make its own connection to the backend IP on the same port for that service. It doesn't see our namespace VIPs because we're not running it inside of our namespace, and there's lots of reasons for that we can talk about offline if we need to, but it's bad. So we're not running it in our namespace. So what I actually did, is I'm using a pair of APIPAs on the inside and the outside and a /30, so it's point to point, to communicate to do some things that are useful. We'll get to in the next paragraph in a second. Go ahead and load it. And we're also clamping our default route and our default source IP. Some traffic is generated from the namespace. So when the namespace gets traffic in and then that traffic is going back out because it's getting denatted or snatted, it has to actually do an ARP lookup itself for the destination it's going to. Now that ARP lookup is going to source from some IP. If you don't give it an IP that will be the default for it to source from, it will source from one of your VIPs randomly, which turns out can actually make everything break. So I have put a specific IP that will always be the same, that will never conflict with anything else inside the namespace, and the same thing outside. They can be identical on both sides. A little bit of tweaking that goes on to make sure that they are never able to route elsewhere. It's pretty easy, but I don't have anything on a slide for it. So we always know what traffic's coming from, where it's going to, when there's a question. When traffic is specifically going to a VIP or specifically coming from a VIP, it will always be those. These are just the defaults for it to fall back on. So this allows us to actually bind HA proxy to this outer one and have it listen on this SAPIPA, and then have it talk to the management IP that all the services are bound on, just like the other ones that are not through HA proxy. Okay, so like I said, very simple, very straightforward. TCP keep alives. So when you move your VIPs, if you didn't have any of this, which would be the perfect way to start, very naive solution, you fail over all of your traffic. The problem that occurs on Linux with local-to-local connections, let me take a step back here. This is why this exists in the first place. When you have a local-to-local connection on Linux, by default, and this is not consistent behavior when you try to modify it on every version of the kernel, but by default, the only consistent behavior is that if you don't specify your source address for a connection, which is 99% of the time, you just connect from, connect to here, the kernel will pick the same address you're going to, the same destination address that you're going to as your source to use. So it is going to be the same address to the same address. So when you have a client on a box that's talking to a service on the same box, and that service is accessible through a VIP, it's going to end up with a connection that's VIP to VIP. Okay. Now when you fail over the VIP, that address is gone from that box, but the connection is still established as far as that client is concerned for that moment, and the service. Turns out, when you remove the source address for a connection, it doesn't behave very well. It actually gets stuck. And if anybody's interested, we can go into the details of how it gets stuck offline, but essentially what happens is when you try to send traffic, the kernel lies to you and says, oh, that connection's busy. It's still active, it's still established, it's good, it's just busy, so you'll have to wait. Unfortunately, what happens when you have, say 35 plus service/client connections to databases and message queues and API servers, and they all think that they're still established when they're not, is everything goes horribly sideways. So the TCP keep alives are serving, number one, the namespace prevents you from the VIP to VIP connection, because it's never local to local, it's always local to somewhere else. So the TCP keep alives, you can still have connections that kind of hang around for a while because they don't send any traffic if they're very idle. So we want to force them to not be idle by turning on TCP keep alives, so that when it does occur, all the existing connections within 10-15 seconds maximum will realize that they need to take a new route, because when we move the VIP, we move the route. And when they take their new route, they're going to get back a TCP reset, because it's going to say, I wasn't talking to you. You're a new machine. You weren't talking to me before, so reset that connection, try again. That's what we want. We want to fail over. So this severs all of our old connections very cleanly. So again, we turn them on. Yeah, that's what I just said. Just said. Wow, I should just actually use my slides. This would be awesome. Yeah. So, as I mentioned, all connections will eventually do this. This just makes it happen faster. Okay, so there's a couple of notes, a couple of issues. This is obviously a lot more complex under the hood, so deep troubleshooting is more difficult. But identifying which actual controller is active. Normally you just do ifconfig, IPA, you look for the IPs. These are my VIPs, cool, they're on this side. Now what you actually have to see is if there's a route for that VIP that's in the global table. So it's not the IP itself, it's the route for it, because it's a route into the namespace. You can also look in the namespace, but as far as a traditional sysadmin, something obvious, you jump on a box, where's the VIPs? You're not going to see them in the IP list. You will see them in the routes. So another drawback. And not every piece of software can be configured for TCP keep alives. So some bits of Quantum and Neutron actually don't have keep alives on all their API connections. They're HA proxy bound connections. So they can actually get stuck. It's a very technical term. Stuck is something that will take me about 15 minutes to draw. So we're going to just say stuck and require a restart of that service, unfortunately, because it's actually a way of getting stuck that never times out. It's awesome. It really is stuck. It's wedged hard. It's very rare. It's very rare, but it can happen. Now you can solve this, if you are happy with LD preloading everything that loads on your whole box with libkeepalive. So every time there's a connection, it hijacks that call and stuffs TCP keep alive on the connection. Problem solved, right? Yeah, we won't spend time talking about LD preloading everything. It's been around a long time. libkeepalive seems pretty stable, but yeah, we'll leave that one there. So benefits, failovers actually work. Woo! Actually work really well, shockingly well this way. That kind of stands on its own. So in the common case, you're going to have pretty quick, clean reconnections on a failover. That's very important with complex service stacks. Again, with replicated message buses, replicated databases, like this kind of stuff really needs to know when side A is down, and that doesn't happen well in the naive approach. Another benefit: no piece of this solution is esoteric. I know you'll probably disagree with me, but what I mean is there's not any one-off software built this today for this purpose. This is all core Linux networking components. Not all of them are very commonly known or commonly used, but they are all well maintained, none of them are experimental, and they are all well understood by people who know of them. So that said, they've been in the kernel a long time. A lot of this stuff, actually all of it, none of it's new. So even network namespaces have been around for 3 years, give or take, since kernel 3.2. So quite a while. So you can have some confidence that what you're actually using is going to be fairly reliable. Also, my notify.sh is actually parameterized. It's fairly flexible. You can generalize and customize as needed if you need to change kind of how things work, like the name of the namespace the VIPs live in, the name of the VETH pair endpoints, whatever works for you. You can even swap out the APIPA for something that you prefer, which you shouldn't do because it's non-routable and that's what you want, but you can. So that is actually in my links at the end, but just to kind of summarize what we've discussed, what I've beaten you with verbally. OpenStack networking is really hard. It really is, especially when it comes to HA. So I think maybe we should update relationship status a little bit, because I think that's more appropriate. And what did I just look at? Like I don't even know what that was. Yeah, that's it's pretty much what we're talking about. So here's some links to read further on this subject. Top one is our chef cookbooks for deploying our opinionated, OpenStack setup. It's RPC. Second one is a direct link to the notify sh script that will hopefully keep you awake many nights after you have read how it works. It's pretty clean, but it does terrible things. And retrofit. Ask me about that afterwards. It's for retrofitting combined control and data plane connections in your infrastructures. It's not really appropriate here. And then a direct link to our actual product if you're interested. And that's it. Are there any questions?
We won't join
Any questions that can be answered in polite company?
Yeah.
Yes.
Do you think Amazon AWS will be subject to storage
Yeah. So to answer politically, no. So Amazon's infrastructure is not really any different. So the going on that's different is they're not using combined load balancers and service controllers. So they have external load balancing as far as VIPs are concerned. So they have their elastic IPs and some other interesting things you can do, standalone load balancers, and those are injected into their infrastructure in a way that you won't see. So the way OpenStack is working here is we're actually talking about, like, you've got 3 boxes, right? Like Amazon's infrastructure, they can afford to plug in automated hardware load balancers if they want, and so do we in our public cloud or even in larger private deployments, whatever you want to do. But really, what I was hoping to tackle was the smallest, viable use case, something that would also continue to allow you to expand. So if you really want to just use hardware load balancers, go for it. Great. You don't need this. And in our cookbooks, you can kind of excise the bits that you don't need as a result. But Amazon, if they had this same construction, would have the exact same issue. It is not endemic to anything we are doing or even OpenStack is doing, in the sense that it's purely how Linux networking works. You make a connection to an IP on the same box, it's going to come from it. If you strip away that IP, it's going to do exactly this. It's just how it works. Any other questions? Yes?
Do you recommend this architecture necessarily?
If you could split them out, why would you not?
Right.
Yeah, so if you can, I would probably recommend splitting them out. It's really just a decision you have to make based on your node count and also your port density, right? Because if you think in data center terms and you have racks and you can only fit so many machines into the racks depending on your actual resource requirements, like you might need X amount of vCPUs and RAM and disk and actual networking, maybe you have 3 storage nets or whatever. Now you have a limited amount of port density available. So if you want to put in new machines that are purely for network controllers to do your load balancing or whatever, or even some hardware load balancers, you have to account for how many ports they're going to take and what kind of bandwidth goes through them. If their aggregate bandwidth is really high, you might not actually be able to use them for your purposes. You might need to have something that's got 12 NICs in it and is also a load balancer. Just depends. Any other questions?
What performance you say because you're connecting really fast?
Mm-hmm.
Can we have a rough idea of what it is?
Failover times? Failover time, how long it takes? Yeah. So there's one piece that takes longer, which is Nova Compute. It is a service that runs on a compute node for Nova, helps communicate with the Nova API server, talks to it about how many resources there are, delegates out tasks for spawning VMs, etc. That one takes up to 90 seconds to fail over. It has nothing to do with this. It does it regardless of what technique you use. However, the vast majority of services and other components and database connections will fail over within 10 seconds at maximum. Usually they're closer to 3-4 seconds, and most of that time is taken in actually running through the scripts and actually doing VIP removal, VRRP sync, because it takes a couple seconds for it to get a new advertisement, wait the amount of time, try a transition. So if you talk about removing the overhead of the infrastructure bits that actually do the failover, it's a couple of seconds. The total absolute amount is usually under 10. And that's for a full failover. That's not for the moment at which it starts to try to make new connections. That's like everything is back up.
Will you look for more controls
To determine whether there's a problem?
to the scale?
Yeah. So what I look at actually, so as I kind of hinted at a little bit, IP route has replaced ifconfig and has actually it's NetTools. It's really, really old and horribly outdated and broken and buggy, and nobody maintains it, except Debian has a patch fork that they kind of are abandoning. So IP Route 2 is the new replacement. It includes a utility called sockstat. The binary name is SS, just like IP Route is binary IP. Sockstat replaces netstat. And sockstat has in it a capability to look at timers that are on connections. Netstead does too, but Sockset actually shows you more real information about what's going on. So what I usually do is SS-ENTP. It gives me all numeric, TCP, show me the process that's involved, and show me extra info like timers. And then I'll grep it or use, it has a little a language that you can, syntax kind of like TCP dump, that you can target connection specifically, but grep, whatever, to look at the ports for the services I care about. So I'll look at 3306 for MySQL, I'll look at 5672 for Rabbit, look at some of the ones for OpenStack I know of, 9696, 9797, whatever. And those are really to see if I have any timers that are in persist, which are the broken connections I was mentioning. If I have any keep alives that are high counters, because it'll show you the time left that it's counting down and the number of cycles it's gone. If it's if there's a bunch of keep alive timers that are all counting down and their increments all 0, great, that's what they should look like. The other thing to look for is send queue and receive queue in your sockstat output or netstat output. Will show you how much data is queued for receiving or sending. And if those queues are larger than a couple dozen bytes for a long period of time, it means that something's broken in the connection. And that's the primary thing you'll see when you fail over in a naive way and you have a broken connection, one that's wedged, is you'll see one of the queues get huge and a persist timer on one of the ends, and basically they don't talk to each other for quite a while, nor do they reset and reconnect. Any other questions?
One, two. All right. Thank you, Evan.
Yeah,
That was
no
amazing.
problem.